Page 40, continuing with separation techniques used in the chemistry laboratory. So the third technique is evaporation. So we typically have some sort of aqueous solution, and so it's separating the components that are dissolved from the solvent in the solution. So we use a couple of ideas. So we use a difference in IMA strength. So that's the attraction strength, those intermolecular attractions. So there's definitely a difference in that. We use a difference in boiling points. So BP difference. So what happens is we end up heating the aqueous solution. So when we heat this aqueous solution, we end up with two results. The solvent, or the water, it changes and it leaves the container, and so it changes into a gas and it escapes. So that should be a G. So the water that was part of the aqueous solution, it leaves the solution as a gas, so it escapes the container. And then the other item that was present in that solution, so I'm just going to put the salt, it reforms as a solid. And so then it forms as a residue or crystals in the bottom. So, all right, residue or crystals, because it'll depend. Sometimes it just looks like a little bit of a trace of something there, and then other times, if there's a lot of salt that's been dissolved, you'll see the more crystalline shape. So a residue or crystals line the bottom of the container. So we can allow this to happen slowly and just leave it out for a few days. That would be the evaporation. Or we could apply heat to encourage the process to happen a little bit faster. So a difference in IMA attractions, forcing it to a gas, reforming as a solid. So here we go. The next technique, if I can move this up, is distillation. And distillation, the chemical or the setup in the lab is a little bit more involved, but the overall idea is pretty simple. So distillation, know this. This is a process that is specifically developed to separate based on a difference in BPs. So a difference in boiling points. And it's specifically used to separate two liquids. So take a look here. We have a mixture that is water and it's alcohol. So the boiling point of pure water, is 100 degrees Celsius. Alcohols tend to have lower boiling points. So the boiling point of the alcohol, I'm going to say, is around 80 degrees Celsius. So the boiling point is the temperature at which you can force a liquid to change to a gas. So a difference. And in this lab, what they do is that you heat the mixture to a temperature that is between the two different boiling points. So heat the mixture to 90 degrees Celsius. So at 90 degrees Celsius, the alcohol will go through a phase change. It'll go from being a liquid to being a gas, whereas the water, it just gets warmer. It is a liquid and it stays in the liquid phase. And so the alcohol, as it changes from a liquid to a gas, it will travel up and then it's forced to fall on down. And so here the alcohol travels through this other tube that's called a condenser, and so it forces it to condense, forcing it to go from a gas back to a liquid because the condenser supplies cooler water surrounding it. So it makes the alcohol vapor temperature drop and it changes back to a liquid. And then we can collect the pure alcohol in a container at the end of the condenser. The last technique here, if I can get this to move up, is chromatography. And chromatography is known as the science of separation. Now, there are all different types of chromatography. This picture here represents the simplest form known as paper chromatography. Then there's thin layer chromatography. There is HPLC chromatography, which is high pressured liquid chromatography. There's GC chromatography, which is gas chromatography. And then from there, you can branch into mass specs. Any form of chromatography has two things in common, is that it has a mobile phase, which literally means some sort of material is actually physically moving across the system, and you have a stationary phase where it is not moving. So in paper chromatography, the paper strip is the stationary phase. And for simple chromatography, water is the mobile phase. So if you just take a piece of paper or paper towel and you just put one corner of it into a pool of water, if you let it set long enough, you know that that water will start moving through the paper, and part of the paper or paper towel that's really far from the water source over time will become damp. So that is what is the mobile phase, is water, a liquid, moving across or through the stationary phase. And so what we do is we put our sample of interest, that is this ink. So this is the sample. And as the water starts to travel, it will travel and hit the ink, and the ink will slowly start to dissolve, and the water will start to carry some of the ink molecules with it. And if you look at your diagram, so you notice that the ink spot is now not as dark as it was, and you can see the different types of molecules are being separated out. And for this particular ink spot, farther from where it started, we end up with yellow molecules, we end up with red molecules, and blue molecules. And you notice that the different colored molecules, the pigments that were used to make this ink spot here, they traveled different distances away from their origin. The blue traveled the farthest and went the most with the water, where the yellow traveled the least with the water. So chromatography takes in two major ideas. So it takes in the level of solubility of the sample with the mobile phase, and something that really impacts the solubility is the polarity. And then the other thing that will also affect how far they travel are the molecule sizes. So is the yellow molecule, it's soluble in water, but is it so big it has a harder time traveling through the stationary phase? So molecule size.